Black body indoors absorbs heat at a net rate of 5 kilowatts. The black body has an area of 1 meter squared. Assuming the indoor enclosed area can be considered black, and assuming the walls are at a temperature of 600 Kelvin, what will be the temperature of the body at equilibrium? So I drew our problem here. I have a black body in here, and then I drew the walls initially to be red, but then they said the walls are black as well, so I put this black paint around the walls. Okay, so that's our situation. What does that matter? Because that when we're talking about black bodies, the emissivity, that's like ideal bodies, the emissivity and its absorption is going to be 100%, right? That's the ideal situation. Now, if we want to know what is the temperature of the black body, okay, if we want to know the temperature of the black body, that's quite simple because we know the Q net will be related to the area of the body, the Stefan-Boltzmann constant, and the difference between the temperatures. We know the temperature of the wall to be 600, right? So we know this is 600. Kelvin. So the only thing we need to answer to be able to solve this problem is the following. Is Q going from this side to this side, or is Q going from this side to this side? And this is a very simple question, but I'd say that it's a 50-50 chance you get it wrong if you don't think about it before you start doing the math. Can any of you guys tell me whether TB is greater than T-wall or T-wall is greater than TB? And if so, why? That is absolutely right. The black body indoors is absorbing heat, right? We know that information there. So for it to be absorbing heat, then that means that Q has to be going like that, right? And if Q is going like that, we know from the zeroth law of thermodynamics that T-wall has to be greater than TB. Why is that important? Because when we get here to this point here, in which we're plugging in the numbers, we can be sure that this one will be T-wall minus TB, right? We can do that. What would be the other option? Well, the other option would be actually have TB and T-wall, so we could do TB and T-wall because we're talking about the black body, and this will be negative, right? But like I said, prefer to avoid the negatives, so we can always do the greater one minus the smaller one. Okay, so then the only unknown becomes T body, and we can solve that quite easily because we have 5,000 watts has to be equal to the area is 1 meter squared. Stefan-Boltzmann equation. You'll find this guy as 5.699 times 10 to the minus 8, or you can also find it at 5 times 6.7. Sorry, 5.67. Both, you can use both. Depending on the textbook that you use, it'll be different. Okay, you can use whichever you find suits you best. 400, and then the unknown is the temperature of the black body. My pro tip here for you guys is leave the square root, not the square root, the fourth root as the last step to do. Don't do it all at once in your calculator because a lot of people go wrong with that. Unit-wise, we have Stefan-Boltzmann, and that will be watts per meter squared per Kelvin to the fourth. So note that our meter squared and our meter squared go away, and our watts go with watts, and then we'll have Kelvin to the fourth, which will become Kelvin when we take the root. So this is TB equals 451.12 Kelvin. And that will be answer for 1. So note that math-wise, this is quite simple. But if you flip this, you're going to get an incorrect answer. Okay, great. So we got A. Let's go to B. Let the temperature found in A be the temperature of the black body. So black body now is 451. If all the heat arriving to the body in A is lost by convection with a heat transfer coefficient of 1,000, remember the good old days? Good old days where you actually got H, you didn't have to calculate it. They're back. Then what is the temperature of the surroundings? So now this situation has pretty much flipped, right? Now we know the temperature of the black body. Oops, we know the temperature of the black body. It's the one that we found before. And what we don't know is the temperature of the wall. That's what we're looking for. So we're going to apply Newton's cooling because we're talking about convection this time, not radiation. And what this guy is saying is that the body is losing. I think I have the word losing somewhere, hopefully. Yeah, right here. Right, so the body is losing energy due to convection. So if it's losing energy, that means that my Q is going away from my body. My Q is going like so. And if that's the case, that can only happen if the temperature of the wall is smaller than the temperature of my black body, right? So that means that when I solve this, when I solve the same 5,000 watts, which is the energy from problem A, for a H of 1,000 in an area of 1 meter squared, then the T body has to be greater than the T wall, right? And so obviously this guy, 1,000 and 1,000. So the difference in temperature is just 5, right? So the difference from T body and T wall is 5 Kelvin. Okay, and again, note this is a 50-50 chance of you getting it wrong if you don't think about this before you do the problem, because if you don't think about where the energy is going, you can't tell me that the temperature is actually greater than the body. So you tell me that T wall is 500 and whatever that would be, 456 instead of our 446. 0.12, well, okay. So that will be the answer for part 2. And be done. Part C. Where's C? Okay, C. You replace the black body with the one that has a temperature of 300 Kelvin and an absorption of 0.1. So only 10% of the energy that arrives to the black body is actually absorbed. If the walls are again at 600 Kelvin, what is the new heat transfer at equilibrium ignoring convection? So now we don't want to know about convection. We're back to radiation, and we want to know what is Q, right? What is the new heat transfer? So what is the heat transfer? So this is a situation on C. I've painted my body slightly blue because now it has an absorption of 10%. The temperature is 300 and the walls is 600. So that's quite straightforward, right? We know Q is going to be flowing from the wall to the black body, and we know Q net in a situation like that. Q net, the energy being transferred, is related to how much the black body can absorb times its area times Stefan-Boltzmann constant times the difference in temperature. So that will be T wall to the 4th minus T body to the 4th. We have everything we need, quite straightforward. Only 10% of it is absorbed. The area is still 1 meter squared. Stefan-Boltzmann equation, its constant still is 5.99 times 10 to the minus 8. And then this is 600, and this is 300. Watts Kelvin to the 4th divided by meter squared, Kelvin to the 4th. Meters squared with meter squared, Kelvin to the 4th. We're left with watts. So Q net equals 300 and, approximately 689 watts. And that will be Q going from the wall to our not so black body now. Any questions?